Good stuff. Okay, so which ones did we want to look at here? Who's got questions that need answers? Four. Oof. I hate this. All right, hang on. I think that's good. Okay, let's see, 4. Oh, this one. Okay, this one actually isn't so terrible, I think. Let me get rid of this. Okay, so like, what is the? Let's see here. What is the approach? I mean, the thing is, like, we've been talking and working with two ideas, right? Like conservation of energy and the work energy theorem. So like, which of those two do we think we want to use here? And why? I feel like, yeah. Okay, wow. Okay, you all said the same thing. That came in fast. Cool. Yeah, exactly. We want to do conservation of energy, and the reason for that is somebody said potential energy is present, which is good, but also the thing is that we have no non-conservative forces doing work, right? So that would be the big, I think, indicator that we want to use conservation of energy. So I'm just going to go through and symbolize things here really quickly. But yeah, so the idea is just to do the stuff. And so we can come up with like the 3 different equations here. So I think that we can talk about first like what's happening in terms of the energy when the roller coaster is like in its sort of initial position, right? It's at height h above the ground, and it has some non-zero speed, right? Now remember that the first thing I want to do, right? I'm not going to do this on the computer, but like if I were solving this by hand, I would definitely want to go through and like indicate where I'm taking my y=0 position to be, right? That's kind of like what we would do with kinematics and Newton's laws, where we would draw our axes. I can just zoom in on a document if that works. You know, if that is that better? But anyway, so we're going to take our y=0 to be the ground here, and it might not seem like such an important decision in this case, but like it you know, not doing this correctly can mess you up. So just be careful. So we have gravitational potential energy and then kinetic energy, right? Not so bad. Now let's call the energy when it's at the top of the hump here E1. Maybe I'm not mature enough for this, but I can't get over the fact that they call this a hump. They could just call it like a half loop or something, right? But let's say that this is E1 here. Now, I don't think it's any secret, right, that we're going to have some gravitational potential energy and kinetic energy there. And I'm not going to call it big R with a full word in the subscript. I'm just going to call it little r, just so we're all clear about that. But there's also kinetic energy there, right? I know my internet is doing weird things. Let me just try this. And then finally, right, let's talk about what's going on here. We want to think about what's happening like right when this thing is at the bottom of the loop here. Now, what forms of energy do we have here at the bottom of the loop? What would be the only one that we have, I guess, is the more direct question. Who can tell me? Yeah, only kinetic, cool. So this looks like this, right? We could call this 1/2 m, 1/2 m v2 squared. And maybe just to be consistent, I'll call this v1. Yeah, so this is what we have, and we know, right, from conservation of energy, we know that E naught equals E1 equals E2. But we need something else here, right? And what we need is the form of Newton's second law for circular motion, right? Because when the car is here at the top of the hump, or really at any point on the loop, it's undergoing circular motion, right? So what I would say is we just need to note that when the car is at the top of the hump, we can write the net force equation in the centripetal direction like this. I mean, we're going to have a normal force, which I'm going to write with this weird n because it's not the same as the n that they give us, right? Minus mg. And we already sort of have said that the velocity or the speed at the top of the hump is v1, right? So from Newton's second law, this should be squared, we can write this. Now this is our centripetal acceleration at that point, right? And we, let's see, we want the centripetal acceleration there to be equal to n, right? Remember, this is a different n than the one I just wrote. And so what we have is we just have that v1 squared over r equals n, right? And we can go through and write then that our, let's see, we write that this is just Rn, right? Because solving this for v1 squared gives us that v1 squared is Rn. And so this is now the form of our expression for the energy at this point, right? And you know, like I'm not gonna probably go through this with or in too much detail, but like similarly for the loop, we're gonna write this. We're gonna write that v sub 2 squared over big R equals big N, right? And then we can adjust this to get it in terms of N and R, right? Because as before, the velocity squared, or the speed squared, I guess I should say, is just R times N. Is this clear? Does this make sense to everybody? Does anybody have any questions about this? What's going on here? Cool. So I'll get you started, right? Like I'm just going to make the computer do the algebra. And then you can do the second part. Let's see here. So why is v squared over r equal to n again? Because circular motion, right? Remember that the condition for circular motion is that the centripetal acceleration is given in general by v squared over r, right? And so they're saying that the centripetal acceleration should be at a maximum some multiple of g for the hump and then some other multiple of g for the loop, right? And so we just want to make a substitution that gets like what we want to solve for into our equations, is all it comes down to. And this here is what somebody's asking about, right? This v1 squared over r equals n. This is just saying that this is the centripetal acceleration. Like maybe I could write this more suggestively. At 1, right? And okay, so the question about the n's, this script n, right? This like fancy n is the normal force. Now I didn't really need to do this because like I don't have to sum the forces to know that the centripetal acceleration should be v1 squared over r, but it's not a bad idea to do, right? It's good practice, I guess. But we could have skipped this, so you know, don't worry too much about this. I just want to make sure the notation is not confusing, or maybe it's more confusing doing it this way. But I'm trying to make it so that it's not. But yeah, okay, so I think that those are good questions. So I think what we can do is we can just see what the solution looks like for the first part, and then I'll let you guys work out the solution for the other part on your own. But I'm just going to make Mathematica solve this equation for me. And I'm just equating energies, right? I'm just going to say that E naught equals E1. So let me try to do this carefully. And we said this equals m times g times r plus 1/2 times m times r times n. And we want to solve this for r, right? Is that what we're solving for? I'm solving for r. Yeah. It looks good. Let me know if you see a mistake as I go through and type this in, of course, but I think that's fine. So we find that r should be 2gh plus v naught squared over 2g plus n. Now you have to remember that this n is not 1.57, like in my case at least, right? You have to remember that this is 1.57 times 9.81 meters per second squared, right? So be careful about that, because I saw lots of students forgetting to do that, and it messed them up. And so this is what we got, right, when we set E naught equal to E1. The next step would be just to set, I'll put this in words, but you set E naught equals to E1 and E naught equals E2. Okay, yeah, so for n, right, like if you look at my numbers, this n is going to be 1.57 times 9.81 meters per second squared, right? Because they're giving you the centripetal acceleration as some multiple of g, which is not an uncommon thing to do. So just don't forget to multiply by 9.81 meters per second squared for n. Does that clear that up? Does it make sense? Cool. Okay, and does everybody feel good about doing the second part, right? It's kind of just the same thing, except the algebra is actually a little bit easier because the equation here is not as, you know, involved as this one, right? So I will just leave you to do that. Cool. Okay. Somebody else then was asking about 10, so we'll look at that next. Let me see here. This one. Well, you did this one last week, right? It's the same one as the previous homework assignment. But yeah, we want to do this a different way now, right? We want to use conservation of energy. I guess last week it was work energy theorem, right? Which, I mean, they're really the same thing, but you know, the approach is, like, I guess a little bit different depending on which one you specifically want to use. So let me just go through and like write out the symbols. We have that m is 3.35 kilograms. V naught is 9.50 meters per second. There is a spring with a spring constant of 71 newtons per meter. And we have a coefficient of friction, right? So this should be a kinetic friction, right? So what was tricky about this? Can somebody tell me? What was like the issue that people were having? I mean, did you just try like conservation of energy and it's just not working for you? Is that the okay, conceptualizing what to solve? Yeah. Okay. Conservation, yeah, okay, those, yeah, so yeah, and that's kind of the point of the problem, right? Is to figure out how to deal with the fact that there's friction. So, uh, because friction is a non-conservative force, when it does work, we have to be careful about how we apply conservation of energy. Now, I don't know what like the textbook gives you in terms of the equation here, but I would write something like this, that the change in energy is just given by the non-conservative work that is done on the object, right? Does this look familiar? Or did he like at least mention some formula like this? Okay, good. I mean, I hope to God that he did. So what we can do is we can just go through and do this sort of step by step, right? So as the block collides with the spring, there's only kinetic energy, right? Because the spring isn't extended or compressed, and we also have like no change of height for the object here, so we don't have to really worry about gravitational potential energy. So what we could do is we could just say E naught is simply the kinetic energy, and that's given by 1/2 m v naught squared, right? Now, what about after the spring is maximally compressed? What does the energy look like there? We'll call this E1. I'll just call it E. What form or forms of energy do I have here when the spring is maximally compressed? Yeah, and the elastic potential, to be specific, right? And so the compression of the spring is the same as the distance the block travels, right? So this is going to be 1/2 k. We'll call it delta x squared. And now the thing is, like, if we tried to just equate the two here, if we tried to write 1/2 m v naught squared equals 1/2 k delta x squared, we would get something that doesn't work because energy is being dissipated by friction. So we account for that by with this, right? So our delta E is going to be 1/2 k delta x squared minus 1/2 m v naught squared, right? And then we just need to fill in what the work is done, what the work is that is being done by the non-conservative force, which is friction in this case, right? So should the work that I put here, do we think it should be negative or positive? Yeah, negative's good. Cool. So we can write the force of friction is just going to be the coefficient times the normal force, which is the same magnitude as the gravitational force, right? And then we have to remember that it's going to act over a distance, right? Because if I don't fill this in, if I don't put delta x here, then I just get that I have a force on the right-hand side, right? And so it's easy to forget to do that, but like this would be a huge thing to be careful about, because if you don't, you're going to write something that doesn't make dimensional sense, right? But we put the delta x there, we're good, because this is a force times a distance, and we got the sign correct too because the displacement is to the right and the friction force has to point to the left, right? And so there's an angle of 180 degrees between the friction force vector and the displacement vector, which means -1, right? Cosine of 180 is -1. So we just have to solve this. And this is going to be quadratic. Yeah, okay, so that's a great question. Somebody's asking, like, why don't we put the force that the spring exerts in there? And the reason is because the spring exerts a conservative force, right? And remember that conservation of energy already accounts for that. So for conservation of energy, we have to just use the work being done by the non-conservative forces. And friction is definitely non-conservative, right? So if you did that, you would be double counting it essentially, because look, when we write E, most generally we write something like this, right? We write 1/2 mv squared for the kinetic energy, not to the 21st, mgy for the gravitational potential energy, and let's say 1/2 k x squared for the elastic potential energy. And we already counted for the elastic potential energy here in the final state, right? So if we did that again, we would have made a mistake, right? We would have written it twice, or accounted for it twice, and we don't want to do that. Does that make sense? Because this is the biggest, probably conceptual issue people will have, and definitely something that you want to be 100% clear on before the next exam, right? Because this would be one of those things where if you don't, realize this, you probably lose a good number of points. And so, just to take like a minute or two here, really quickly, I'm gonna write out the work energy theorem for all of us to look at, right? And the point is that we want to use one of these or the other. We don't want to try to combine them in some, unholy way, right? Because that's how we make mistakes, and that's how we like double count what's going on, say with like the spring or the gravitational force, right? So just remember that conservation of energy cares only about the work being done by non-conservative forces, providing that you account for the kinetic energy, gravitational potential energy, and elastic potential energy at every step. Whereas the work energy theorem cares about all the work being done, right? But last week when we did this with the work energy theorem, we got the exact same result. So I think the point of this is just to show you that they both work, right? Do people feel good about solving this? Because I could like probably just do the symbolic form if people don't want to do the annoying quadratic stuff. What do we think? Do we want that? Well, okay, nobody's saying anything, so I'll just assume that you're all good with doing the quadratic stuff. This is what you have to solve, though, right? And it should be more or less the same equation that you got last week for the homework. I think this is good. Cool. Yeah, I mean, you can just make a calculator do it, right? If you want to plug in the numbers for everything except for delta x, and then it's not so bad. Cool. Okay, is everybody good with this one? And I'll just ask, like, if you want to look at another one, just let me know which one that is, and we can move on. Cool. Good. Okay, noise. 7. Let's see what's going on with 7. Oh, this one's kind of stupid, but yeah, okay. Yeah. Okay. So the usual, shenanigans. I'm just gonna go through and write out my symbols. Let's see here. I will call the maximum compression of the spring, I'm gonna call it L. And for me, that's 0.413 meters, right? We have a spring constant, which is 835 newtons per meter. So let's say lowercase h is the height above the ground, and big H is the depth, right? He's like a complete weirdo who's standing in a pit throwing balls in the air, and the pit is 14.1 meters deep, I guess. Yeah, good for him. Okay. So what about this one, right? Do we think that we want to use the work energy theorem or conservation of energy? Does anybody have an idea? So this is kind of a trick question because we actually want to use both. So yeah, so we have to kind of, let's see, how do I explain this? So the work that he does as he throws the ball, right? Let me put this in words in the document. The work that he does as he throws the ball gives the ball a change in kinetic energy. And so the reason that I'm not sure that I like this problem is because, like, let's look at the net work that is being done on the ball, right? So we're imagining that he's got it in his hand and it's just like, at rest at some height above the ground. Then he moves his arm and the height of the ball changes as he exerts a force on it to throw it up, right? So it feels like there should be work done by gravity because there is a displacement in the vertical direction, and obviously the gravitational force points downward, right? And then there should be the work that he does on it to impart this change in kinetic energy, right? And the change in kinetic energy is just, we'll call it delta K, and then it's just 1/2 m v naught squared minus 0, because we're going to say that the ball starts at rest before he begins to throw it, which is, I think, a sensible thing to say. Now this, like, we just have to neglect this because we don't have any information to calculate this, right? We would have to know the change in height of the ball as it is thrown, and we don't. We're not told what that is, so we're just going to get rid of this. We're going to neglect it, even though maybe it feels like we should have it, and I think we kind of should, but whatever. So this is then saying, right, just that the work that he does on it is equal to its initial kinetic energy for the second part, in essence, right? Now is the point that we apply conservation of energy. And so we want to say, so we apply conservation of energy because after the ball leaves his hand, if we're neglecting air resistance, there are no non-conservative forces that are doing work on the ball, right? Because there's no drag or air resistance. So now that we've kind of, used the work energy theorem to see how we're going to get the work that he does on the ball, we can just go through and do conservation of energy. So the ball's initial kinetic energy will just be 1/2 m v naught squared, right? Now, if I take my y equals 0 to be ground level, then the gravitational potential energy that the ball has at this point is negative mg big H, right? Because you can have negative gravitational potential energy, right? There's no reason you can't. And the bigger idea here is that it's that only a change in gravitational potential energy is meaningful, not a specific value in and of itself, right? So this is my initial energy. Then we can just kind of look at what the final energy is. Now, this will be, if we're thinking, right, if we're thinking about like the point where the spring is maximally compressed, then we know we'll have gravitational potential energy because this spring is like situated above the ground, right, above ground level. But what would be the other form of energy that we want to put in here? Yeah, elastic, right? Because there is the spring and it's been compressed. So we would write 1/2 k L squared, right? So if we want to be fancy, we could do this just symbolically, right? We could say, well, we have this term here. Why don't we just call that the work that he does? Because that's what it is, right? And then we set, we just equate the energies, right? And we find that it should just be the work that he does minus mg big H equals mg little h plus 1/2 k L squared, right? We just solve this for the work that he does, and it's not bad. We basically just add mg big H to both sides. Does everybody see this? Is this clear? Is it making sense? Now we made some assumptions, right? Like we made an assumption about the tube, and that assumption is that it's like sort of horizontal, right? Because I don't know, he throws it through a window, and so I guess I don't know, it's like on the ledge or whatever's happening here. But just note that that was an assumption, right? Because it's easy to forget, for instance, when you have like a spring that is situated vertically, that the gravitational potential energy of an object that's like on the spring will change with the compression or extension of the spring, right? I think everybody understands that, and it makes sense when I say it, but it's easy to forget to do that. But we don't have to worry about that here because we are assuming, and I think it's correct, that the spring is situated horizontally. Cool. Does this all make sense? Is everybody good with this one? Any questions? Cool, cool. Okay. Are there any other ones that people wanted to look at? Or are we gonna end here? Cool. Everybody's good. Okay. Then okay, number 6. We can look at that then. Then we'll probably call it, but let's just knock this out. Robert has just bought a new model rocket and is trying to measure its flight characteristics. The rocket engine claims, blah, 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 okay. Travels straight up. There's some height, there's another height, and a mass. Okay, let's talk about this one in just kind of generally. Which idea do we want to use? Do we want to use the work energy theorem here or conservation of energy? What are we thinking? Yeah, and I guess you could use you could also use conservation of energy here, like directly. This is one of the ones where I think it's kind of just, you know, up to you. But we'll do work energy theorem. Now, the thing is, we have to realize, right, that the rocket starts at rest because, like, the engine kicks in at time t equals 0, right? But that means at time t equals 0, there is no velocity and therefore no kinetic energy. Then now think about when the rocket reaches its maximum height, right? We know that the y velocity of a projectile goes to 0 when an object is at its maximum height. And so because this thing is just going straight up and then straight back down, there's not any kinetic energy at the top, right? So what I'm trying to say is that delta K is just 0 minus 0, right? Which is 0, of course. So then we just need to account for, well, let me write this too. Just to remind everybody that by the work energy theorem, this is the net work done on the object. And we need to account for all the works, right? Because that's what the work energy theorem demands. Now, I'll just tell you, we have the gravitational force doing work, right? We have the force of the engine doing work. And then we also have the drag force, right? So which of those is negative? Which of those is going to give us negative work? We'll call this work of gravity, work of thrust, I guess, and then the work of the drag force. Yeah, good. Gravity and drag will be negative, right? So when you evaluate they'll be negative. This one and nope, not that one, sorry. This one, the drag. Cool. So we just have to fill this in, right? Like explicitly. Let me just do that here. So the work done by the gravitational force will be over the whole trajectory, or I guess like half trajectory if you think about it coming back down. But what that means is that it's just the gravitational force times the maximum height this thing reaches, right? Now the work of the engine or the thrust is going to be multiplied by the smaller height because the engine isn't going for the entire trip, right? It cuts out at 19 meters. So that's what our work would look like for the engine. And then the last thing would be to just write that the drag force does work, and it's indicated by this, because this is what we want to solve for anyway, right? So we don't need to like try to plug in the drag force or anything like that. And furthermore, we couldn't plug in for the drag force because it's not constant, right? So remembering what we just said about the change in kinetic energy, this equals 0. And so the equation that we want to solve is just this. And as Connor said, we should find when we do this that the work done by the drag force is a negative number, right? Because the drag force always opposes the velocity of the object. So you just got to solve this. So this one isn't so bad. I think it looks more complicated than it actually is. Is everybody good with this one? Were there any questions about what just happened? Cool. All right, I will open it up once more for questions, but if not, everybody, I was going to say you're free to go, but you didn't have to be here in the first place. So, yeah, if you are going to go, just do me a favor and hit follow really quickly, please. I'd appreciate that. And if you have any more questions, we could probably look at one more, but if not, we can just end it here. Everybody good? Cool. Okay. If you need anything, you know how to reach me, right? So just don't be shy, and I will see you all next week.